Hello and welcome back to Precalculus1. This is section 3.2 and we will be talking about logarithmic functions. These are very important functions. They are inverse of exponential functions and they work together. We'll see how all of that clicks together once we go through first the placement and the need for something like logarithmic functions. I like to put up like a map of all arithmetic operations and show you which bit fits where in terms of mathematics, and hopefully that will get you to appreciate and learn more about logarithmic functions. So the first thing is, as I usually do, 2 plus 3 is 5. And then I can say 5 minus 3 is 2, and 5 minus 2 is 3. So we have mathematical operation, and then we have the somewhat opposite mathematical operation, which is able to retrieve these two input numbers, right, one at a time. So there is an operation and a backwards operation. Now, the fast addition, repeated addition, is called multiplication. So 2 times 3 is 6. And then I'm able to divide 6 by 3 and get 2. And divide 6 by 2 to retrieve 3. So again, we can retrieve both of our input numbers, in this case factors, and we have operation which is opposite, and it's called division. And now we're going to have one more step over here, which will be fast repeated multiplication, which are called exponents. 2 cubed is equal to 8, because 2 times 2 is 4 times another 2 is 8. Now we can retrieve 2 if we quickly take the cube root of 8, right? And cube root of 8 is 2. And the question is obviously, how do we compute, how do we retrieve 3? Right? What do I do to retrieve 3? And that is obtained by this new operation called logarithms. So the notation will be something like this: log, which is short for logarithm, of base 2 of 8 is going to be 3. And today we are focusing on this. So before you freak out, letters, right? Well, yeah, I understand. Yes, I would vote for a cute symbol like we have for all other operations, but this is something that it's, almost 500 years old, and we don't get to change it now. So technically, log is mathematical operation that when you combine with the log, the 2 and 8, you get 3 on the other side. Now, what is the meaning of the log function? And this is where we are going to learn where they come from. Well, if you have a to the b equal to c, which is the exponential form, you can convert that into a log of same base a of c equals b. This is known as conversion, and you will pretty much use this in every problem you see in chapter 3. And this formula will follow you through the rest of your mathematical career. So very, very, very frequent. Now let's talk about this. Right, at some point you learned and memorized some things in mathematics, so let's do the same now. What do you have? You have 5 cubed is 125. Well, that means that log 5 of 125 is 3. Just use the conversion. 3 to the 4th is 81. That means that log 3 of 81 is 4. Ten to the 6th power is 1,000,000. That means that log base 10 of 1,000,000 is 6. So, as you can see, every time you have exponential and logarithmic form, you have the same numbers in a game that are arranged differently. So we would like to learn, right, how to deal with these things. Now, again, we have 3 more sections to cover in this chapter, and we'll go more in depth about properties of logarithms and stuff. That's next class, right? Sometime next week. What we are focusing on right now is learning new mathematical operation that you haven't used before. So you know the way to add. You memorize that 7 plus 5 is 12. You know that you memorized 4 times 6, right? It's 24. You memorize that 12 divided by 6 is 2. You memorize that 3 squared is 9. You memorize that the cube root of 8 is 2. And now we're learning some logs. And they belong, as you can see up there, right? They belong to the list of, mathematical operations that it's a mathematical operation which you put on these 2 numbers and you get an answer. Pretty much everything else did the same thing. You have 2 numbers in the input and some kind of operation, and you get a number in the output. So the log is not different than addition. It does the same thing. It computes a value. It just works differently. Well, we can also argue that subtraction works differently than addition, multiplication works differently than subtraction, and so on, right? So the idea here is to learn this new operation, but the cool thing is that that new operation is related to what we already know. So if you are to, try and figure out how much is log base 4 of 256. And that's some unknown quantity. Well, you can set that unknown quantity to unknown value x and then use conversion, and hopefully that can help. Because now you will get 4 to the x is 256. Now, is there a way for us to solve this without going into some, very, not complex, it's just, is there a way for us to solve this without learning about exponential and logarithmic equations, which is 3.4? And the answer is yes, right? We can do this, because you have to ask yourself, can I make these 2 sides to look the same, right? So you say, can I make this 256 to be 4 onto some exponent here. And that's very easy to check. You go 4 times 4 is 16. 16 times 4 is 64. And then 64 times 4 is 256. Oh, I did that 4 times. So 4 to the x is equal to 4 to the 4. And there it is, x equals 4. So now we found out, over here that that's 4. So log base 4 of 256 is equal to 4 because 4 raised to the 4 is 256. So what you are getting as the answer in the log calculation is the exponent, right? The value of the exponent. That's what you get. So we want to now learn what we can, not just computation, right? But we want to learn also about the function. Let's finish computation first. So right now we are exploring log of some base a of a number, and that's equal to some value, right? That's what we are exploring. If you take a look at your calculator is going to have a button that has log on it, and then another button that has capital Ln. And both of those are actually log. But before we get there, right, I want to dissect one more time this thing over here and say that this over here is read as a base, right? And this one over here is the number. The obviously c is on the other side is the exponent. So, I mean the solution, right? Which is the exponent 20. And if you are to convert in this form right here, then a to the c equals b. If you convert that one, the way I wrote it. All right. Now, a is a real number. And you see that's a base for the log. Could be negative, could be positive, could be 0, could be fraction, right? So any number you can possibly think of. And there are two special values that we work with because most of our sciences fall into those two categories right there. So one of them is the base 10. So log base 10 of some value. Well, we have a lazy notation for that one. We just don't write the base. So if there is no base on log, base is 10. So that is very important to know. And in the calculator, that will be the button that has capital LOG on it. And the next one, the special one, is base E. You know that special number we learned last class? The irrational number? E. So yeah, that one also has the special, and it's called ln. So that's the natural, we call it natural log. And that's your ln button on a calculator. Now, if you study the calculator closely, you see that other logs do not exist. There is no base 2 on the calculator, there is no base 7, there is no base 1.5, right? You just have capital L of G, which is base 10, and then ln, which is base E. And that's all we have on the calculator. So now, can we compute other bases? Can we compute log 2 of 8 on the calculator? And the answer is actually yes, but we have to use a formula for it. The reason why calculators don't have those the button for you to push any base you want is because it's useless. And I mean, it is useless. Most of the all of the applications that I know of in mathematics and physics and engineering, all of them, they're base E, and then some portion are base 10. And I have never seen in 25 years of math, right? I have never seen a mathematical model of base 7 or base 9 or base 1/2. I've just never seen them. So because of that, we don't really need a button for it on the calculator. But, being that you're in a math class, you might be interested in what if I want to do this thing on the calculator. But before we go to the different base, let's just, do a couple of these log questions on the calculator. So, time for the calculator. We want to calculate log base 10 of 93. Well, what you need to punch in the calculator is the LOG button, and then there will be a 93, and then you just close the parenthesis, right? And you are going to get, right, for log of 93, you are going to get 1.968482949. Obviously, it's cut off with decimals. It will be going forever. Oh, actually, it's not equal, it's enter. That's what you use on a calculator. Now, guys, you will have to use calculator in chapter 3. Because chapter 3, right, these exponential and logarithmic calculations, they are not really computation friendly. So we keep calculator close at all times in chapter 3. So if you have base 10, you are using LOG button. So LOG button is for base 10. Now, if you need to calculate ln of, 16, you will punch that in the calculator as ln and then 16 in parentheses, and you push enter. And ln 16 is going to produce the value of 2.77 2588 722, and that's also cut off. It will be going forever. Now, in practice, we keep about 2 to 4 decimals depending on application. 2 to 4 decimals. We don't have to keep a lot of them, but we do have to keep in mind that the error accumulates in calculations quickly with exponential, right? Because we've seen last class that exponential functions rise very quickly. And because they grow very quickly, that means that any error that you have for calculation is also going to grow quickly. So if you don't have about 3, 4, 5 decimals, then the error could compound, to use one of the words from last class, and you might end up with something that has so much error that it's completely useless at the end of the calculation. So we keep about 4 significant decimals. We'll talk more about that we'll talk about it last class as well, right? That's the non-zero ones. Okay, so now, how do we calculate anything? And that will be change of base formula. So log of any base of any number is log(b) divided by log(a), or you can also use ln b over ln a. So that's also something that you can do. Now, sorry, I did not have the stream on, and I just turned the stream on and I see a question. Could you have log of 0, or it's like a division? I will address that right after this base. So yeah, I'll be addressing that question very quickly. So now we have this change of base formula, and this change of base formula allows me to calculate log 7 of 213. Just to toss in any numbers. So I can't compute this on the calculator because I do not have the button for base 7. I only have buttons for base 10 and base E. Those are the only 2 buttons that I have. So I will convert this into log 213 divided by log 7. So log 213, and then you have to close the parenthesis, and then you divide that by the log of 7, and you close parenthesis. The answer should be 2.7552 if you keep 4 decimals. Now, it's very important to close these parentheses, otherwise the answer will come out wrong. If you do not close these parentheses, especially that one, then the problem thinks that you are going log 213 divided by log of 7. And clearly that's going to give us a wrong answer, right? Because the calculator is using PEMDAS. So make sure you are closing parentheses as you are plugging these values into your calculator. So I'm going to give you another one to try. So log base 4 of 1342, whatever. So I will wait for you to solve that. Okay, I'm going to use ln this time around, right? It's okay to use ln. So ln of 1342 divided by ln of 4. We have to get the same. Doesn't matter. You either push both LOGs or both ln's. You cannot mix them. So here we go. ln or log, whatever, 1342, close the parenthesis. Make sure you close the parenthesis after 1342. Divide that by ln of 4, close the parenthesis, and yep, you got it. 5.1951. Good. Now you can have 3 decimals. It's okay. You can have 5, right? I'm not picky about that right now. We'll have to be careful when we do calculations for word problems later. Right now, just getting the hang of the calculator, making sure that you're closing the parentheses so you can get the answers that are supposed to be there. Great. Well, so far we know a couple of things here, right? We know conversion factor, and you can use this back and forth. We also know that log is operation, right? And we also know that log base 10 of a number is just log x without it. And then we also have that log with base e is actually just ln. So you can literally think of these two as a lazy notation, okay? A lazy notation. Why is a lazy notation? Because it's less numbers and letters to write. That's all it is, right? If you compare these two, you are not writing 10, so you're saving 2 characters. Over here you have 5 characters, you have 3, so you're saving 2 characters again. So if you want to think of it as lazy notation, go ahead, right? But 10 and E are special, right? Because they give us sciences. And the rest of the bases are useless and we don't have them. Just they're nowhere in application. But we can deal with those using the change of base formula, where you take log of any base and any number and you just go log b over log a or ln b over ln a, right? Depending on which one you prefer on the calculator. Now, the more the better calculators, the more professional calculators, right, will have less and less. So you will see that some calculators, the super on the end of the spectrum, right, are going to have only one ln button, right? So either log or ln. They're not even going to have both of these bases, right? Because you can express either one of these in the terms of the other. So some calculators go as far as just providing one button, and on some calculators that's ln, on other calculators that will be just log. Now log, which is a base 10, will be used in waves, so you will see that in physics, you will see that in chemistry for calculating pH values. So if you are any kind of student that goes in medical or biology or chemistry or chemical engineering or so on, right, you're going to be calculating those pH values and so on. You will be using log base 10. Now for the physics, right, we are going to have also log base 10 for waves, which are the sound and the earthquakes and a whole bunch of other stuff that involve waves. So that's going to be log base 10. The intensity of the sound, which are the decibels, which is of how loud, the loudness, how loud the sound is. That's also going to be log base 10. But then you have the whole world of, we will see in 3.5, mathematical growth and decay. We talked about garbage, we talked about medication, the bloodstream, the metabolizing drugs in the bloodstream. We talked about carbon dating for history and archaeology. So all of these things, right, we talked about the money. Pretty much everything else is going to be E. And that will be related to our ln button. So it's kind of very structured. Now to answer the questions on zeros and things like that, and we can move finally to talk about logarithmic function. I haven't talked about logarithmic function yet. We are setting up logs because we haven't had logs before. So these formulas I called cute formulas. Log of any base of 1 will always give you 0. So log 3 of 1 is 0, log 1/2 of 1 is 0, and so on. Why does that work? Well, remember what your conversion is, right? 3 is the base, 0 is the exponent, and you get 1. Well, that's 1 equal 1. Cool. 1/2 is the base, 0 is the exponent, and you get, again, 1 on the other end. So this formula makes sense. So log of any base of 1 is 0. That means that log 1 is 0. That means that ln of 1 is 0. Because even those two are special because they model so much of the world around us. Even though they're special, they're still abiding by the rule that if the argument is 1, the answer would be 0. By the way, when I say the word argument, I mean the thing inside the log, right? Because the log can have a number, can have a function, right? Can have another, logs can have, we'll see when you get there, but make sure that log of 1 is 0 and ln of 1 is 0, and then log of any base, not just these two. These are special cases when a is 10 and a is e. A is e. But you can have any, literally any. The second formula, what I call cute formula, is that log a of a is 1. Which should make sense as well, but we'll get there. Log 3 of 3 is 1. Log half of half is 1. Why? Because 3 raised to the first power is 3. 1/2 raised to the first power is 1/2. So these are the cool formulas. Now I know that the question was, what if the 0 is here? We'll deal with that. Right now, let's put the 0 on the other end, and we are getting closer. Because in order for us to understand what's happening when there is a 0 there, we have to first talk about basics of our function here. What about log base 1 of 1? Well, think about it. It's going to be 1, right? Because you have a 1 and you have a 1, and those are the same because 1 is equal to 1. It has to return whatever is in the formula, right? If this over here was, I don't know, a square, then log 1 of 1 would be a square. Because when you have log 1 of 1, you are going to get 1. Why? If this is your log of b of a, well, let's write the conversion aside. A to the b equals c, log of log a of c is b. So when you compare these two, you get that a is equal to 1 and c is equal to 1. And now you can plug those in there, and you get that 1 to some power b is equal to 1. So that b better be 1 because 1 to the 1 is 1. But it's also 2 and 3 and 4, and right? But, you know. So, interesting questions, guys. Nice. But by this formula, it's 1. All right, let's talk about logarithmic function. Logarithmic function. So now we learned that log is like a mathematical operation, right? It's inverse of exponential function, so it is going to have the same numbers as the exponential function. They're just going to be in different spots because notation is different. So how do we create logarithmic function? Well, how do you create any of the other functions? Remember when you had 2 plus 3 equals 5? Well, if you just say x plus 3, you just created a polynomial function. When you had 2 times 3 equals 6, you can just say, hey, 2x. Right? You are replacing one of these numbers with a variable x that can take a lot of numbers as input, and you are creating a function. So if you had log 2 of, I don't know, 16, whatever, you can create a function by saying log 2 of x. Now it's important for us to understand this as we are building up to answering the question, what if instead of 16 we have a 0? We are getting there, right? All right, so let's come up with some of these functions, right? Let's see what can we have here. So say you have what should we do? Let's define and check what these functions are. So let's define them and check the properties. So y equals log base a of x. So this is called logarithmic function. Logarithmic function. And what do you do with it? Well, let's see all the specs of logarithmic function. First of all, this logarithmic function can be turned into exponential function by using the conversion factor. We're not going to do it, but you can, right? It's a to the y equals x. We'll deal with that stuff later. So what do I have here? When I have a logarithmic function, I'm going to show you the graph . So this would be the graph going through 1, x, y. This, as you can see, is going to be, I'm going to erase this, a mirror of e to the x, or I mean b to the x, exponential function. Now, how do I get this graph? Well, you get the graph by, remember what the inverse functions do. You have a function and then you swap x and y for the function, and then you get the inverse. So we can create this graph by flipping the values for, let's say, 2 to the x. And we would graph exactly what you see here. So I will show that later. Let me go through the specs of this graph, and then we're going to graph a couple of those and make sure you know how to get them. So the first order of business is domain. That should all be red now. We see that there's nothing on this side of the graph. So domain starts at 0 and goes to infinity. 0 is not included. Now, why is 0 not included? 0 is not included because there is a vertical asymptote at x equals 0. Do we see that the ln is following the axis? Well, that means there has to be a vertical asymptote there. Now, if you have a vertical asymptote, you cannot have a value at the same point, which is why we're using parenthesis rather than the square bracket. Square bracket means include, and the parenthesis means exclude the endpoint. So because we have a vertical asymptote, here at x equals 0, 0 cannot be included in the domain because, right, if you plug in a value, you will get negative infinity. Range is another basic concept we need to know for all of our functions. And the range for this one is from negative infinity to positive infinity. X-intercept. Well, clearly we have it at x equal 1, so 1, 0. And y-intercept. In this case, none. I say basic case, default case, whatever. Because clearly if I shift it to the left, I'm going to create a y-intercept, right? If I move this graph to the left, it will cut through y-axis somewhere. My same graph look like that? See, it cuts through y-axis. So we have to be careful about, default case is a little bit different than other cases, right? So these are the base. Oh, and no symmetry. Let's put all of this in the box as insanely important. And now I would like to show f of x equals 2 to the x and we know what that graph looks like. But that's not what we're interested in here. We're interested in actually computing the values and swapping them so we can graph our ln. So if I come up with a chart of values with x and a y, we pick x's, we compute y's, and then we plot those. So what are the good values? -2, -1, 0, 1, 2. So 2 to the -1/2 is a quarter. 2 to the -2 is 1/4. Why? Well, 2 to the negative 2 is 1 over 2 squared, which is 1 over 4. Alright, so now that's a quarter, then we have a half, then we have 1, then we have 2, then we have 4. And you can find these values on my graph, right? Negative 2, negative 1. You see this is halfway through over here, and this is below at 1/4. Now, what color? Purple. For inverse, in this case log, we switch x with y. So I'm going to just do a new chart, but now it's 1/4 with negative 2, 1/2 with negative 1, 1 with 0, 2 with 1, and 2 with 4. No, 4 and 2. And how you plot those? So what do I have? I have x is 1/4 and y is a negative 2. That's going to be somewhere over here. Then we have a half and negative 1. Zero, 1, 2, and 1, and then 1, 2, 3, 4, and 2. There we go. Woohoo! So look at the shape. It's exactly what I had before. So this would be log base 2 of x. Now, just like what we had for our exponential friends, right? It's not humanly possible to do the amazing job on these graphs. That we just need to get the general shape, and then you can. If you have more of these, obviously, do they go closer to x, closer to y axis? I'm going to leave that for the YouTube video, right, for you to answer. Or sorry, not YouTube video, Desmos, right? You plug a couple of them, so log base 3 of x, log base 7 of x, log base 10 of x, and then it will give you the formulas, and then you see, right, the way they're impacted as you study this. Cool. Before I answer the question from the chat, it's time for us to talk about what happens if you have log of 0. That question was asked long time ago, and now we are finally able to answer it now that we have a graph, right? And then we can move to the next. And then the next question from Max is the one that is the natural progression for the lecture. All right, so going back now, the question in chat was, what about log base a of 0? So that was the question. And I'm immediately going to tell you that that's equal to negative infinity. You can say undefined, you can say error in a calculator, you can say whatever you want, but the answer is negative infinity, because going to for this input value to be 0, that means you are going towards 0. Now, as you are going towards x equals 0, what is happening with all of the y values? They shoot forever downwards into negative infinity. So, if you have, this is mathematically, not correct notation. The formula that I should be writing is the limit as x goes to 0 of log base a of x is equal to negative infinity. That would be the correct mathematical notation, but we don't deal with limits in pre-calculus. So I just have to do this, and then as usual, when I write something that is not mathematically sound, I put the quotation marks on it. But if you get a 0 inside log, or ln or whatever, right, your answer should be negative infinity, or you can say undefined or whatever. So that's the question answered regarding the 0. Now, the next part over here is transformational functions. So here we are going back to 1.6 and answering Max's question as well at the same time, because the question says, will that line ever cross the x-axis? And it says again, right? Well, if you shift the graph to the left, it's definitely going to cross. It has to cross x-axis, right? I was talking about the y-intercept. Wait, will that line... this question might be if this line will ever cross x-axis again. As if, is it going to bend? The answer is no. This is increasing function, so it goes up. Now I understand better what you asked. So this is an increasing function, and increasing function will not bend down, right? Because in that case, if it bends down to meet the x-axis again, it would stop being increasing function. So yeah. All right, so let's do transformations. And I'm gonna put 1.6 again, because technically that's what we're doing. You can have your y equals log a of x plus minus a number c, plus c up minus c down. There is no surprise here. Same rules that follow x squared will follow logs. Why? Because they're all functions. 1.6 are rules of functions. They are not rules of particular type of a function. They are rules for all functions that you can possibly think of. And because they are rules of all functions, they also apply to logs. That is something that you have to understand. So we had those rules for polynomials. We had those rules for your exponential functions last class. Now we have the same rules for logs. Now, we can also add and subtract c directly to x, which is going to shift that left and right. So log a, and then I have x plus minus c. In this case, plus c is left, and minus c is right. Nothing changes, right? All of the rules that you learned in 1.6 still stay the same, except now you're applying them to logs. Y equals c log a of x. Well, that's going to be, right, stretch or a shrink, like that. Then we have y equals negative log a of x, reflection, on, now what axis are we reflecting on? you put the minus on the whole problem, which is the minus that it's equivalent to being applied only to the y values. So this is reflection on x-axis. And y equals log a of negative x, right, with the negative is inside in the argument, then it's reflection on y-axis. So these are the, right, there is also horizontal and so on. Now, again, I'm just going to stress one more time that, let's go blue notation. Log base a of b, this over here is called the argument of the log, right? Argument of the log. So when I mention the argument, you know exactly what I mean. It's whatever follows the ln, right, or log or whatever else. All right, let's graph some. I should have written graph. And we have, well, let's go with y equals, right, to be official, or f of x. How about that? F of x equals log x plus 1 minus 3. So what now? Well, just like in all of the previous, right? This is, oops, down 3. And this is left 1. To graph this, you can use the x-intercept as the anchor to figure out where the rest of the graph goes. So you have xy, and you have your basic, let's go through here. This is ln x, right? No one cares about that one. Sad, right? Actually, it's not ln x, it's log base 10 of x. To match this, because it's not ln, you can't have ln on the bottom. I mean, you can, but there's just a nasty calculation. So this over here is your anchor point, 1, 0. What are you supposed to do? You are supposed to move it 1 unit left, 1 unit left, and, oh, sorry, I used this is my 1, this is my 0. So 1 unit left and 3 units down. Now, since everything moves to the left, vertical asymptote moves left 1 as well. You can't leave the vertical asymptote behind, right? Everything moves. So the asymptote that used to be on the y-axis is now here. At negative 1. And here, right, here is where the intercept is. So the answer, we're going to come in, go through this one, and then bend and become sluggish and lazy. So the same idea of shifting left, shifting right, up and down, reflections, all of that is preserved. Let's take a look at something with reflections. So, graph f of x equals to 3 ln of 2 minus x. Oh, did I forget to move? Oh, I did. Oh, boo. I forgot to move down. Yeah, drawing these into one, I gotta fix this now. I don't have enough room for the larger graph, so I'm going to fix this. So yes, you're right. Let's go from scratch. 1, 2, 3. -1, -2, -3. -1, -2, -3, -4. -5, dot, dot, dot. And we have all the numbers above. Now, my original function, I'll draw that dashed now. And that's ln x. We are supposed to go one left, and that will make a new asymptote. Oh my god. That was terrible. I hope no one's seen anything. And we shift it down. Yeah, we do shift it down. I made a mistake. So once we shift this, we shift one left, and then we go down 3. So, let's move this nonsense above. So here. It is the same shape as the one up there, because it's the same type of a function. It is ln of x plus 1 minus 3. Except it's moved, and as you can see, we created a y-intercept which we didn't have before. Now, there will be x-intercept, because this thing will keep rising and rising and rising, and eventually will cross the x-axis. So it's only asymptotic on the vertical side, right? The horizontal sides are not. Okay, so now that we fixed this problem, which had 2 shifts, one to the left and one down, and thank you for pointing that out, let's go and deal with reflections. Now, this one doesn't look like it has a reflection, but it does have a reflection, right? See, it's negative x. So that's a reflection on y. So negative x is a reflection on y. So let's solve this. F of x is 3 times ln of negative x plus 2. All I have done is I rearranged the terms, so x is first and the number is second. And now I am supposed to factor out negative. So f of x is going to be 3 ln, and now I factor out negative sign. Come on. Factor out negative over here, and we are left with x minus 2. All right, so number 3 is a stretch. So functions that look like this would now look like that, right? Because it's times 3 for every y value. But this is what it's important. Reflection on y-axis. And then we also have this -2, which is the shift right. All right, so try to draw this one on your own. Now, if you remember from 1.6, I mentioned do reflections first and then deal with the rest. So you draw your basic graph, then you reflect that graph, and then if you have to move it, move it. Okay, let's take a look. So I'm going to draw the basic graph first. So this is just our ln x, right? Nothing special there. And then I'm going to reflect this one on y-axis. Now, when I reflect this one on y-axis, it's going to look like this, going through -1. So this is ln of -x. And now I shift 2 units to the right. And we can stretch it 3 as well. So my asymptote is always on the y-axis until you shift left and right. So now we shifted right 2 units. So my asymptote that used to be on the y is going to be now at 2. Which means that the point here also shifts 2 units to the right, which means it goes from here there. And now we draw the graph that goes something like this. It has to be, right, the other one would curve more this way, but because it's times 3, it should curve more up. This is terrible. I can't bend my arm to draw this. Something like this. It's terrible, but there we go. Goes through 1. Now, if you don't trust me, just go on Desmos, type it in, right? Now, very important thing to address, and this is, it pops up on tests and finals, and then more importantly, it pops up later on in calculus. Plus over there, right? But it's shift right. Note that we factor the minus. You cannot have this form, because numbers are added or subtracted from x, not from -x. So where did I write that? Here. You see? Plus minus c on x. So you have to have x. If that's a minus x plus minus c, then it doesn't fit this. It's not it, right? So we factor out -1. Where is it? We factor out -1, and now it's just positive x there, but because we factored out the minus, then it changed this plus into a minus here. Just go ahead and distribute, right? That will give you -x and will make you positive 2, right? So that's how this turned out to be shift to the right. We can have this in literally any 1.6 problem, right? I just wanted to make sure that you see this one. Cool. So now that you have seen 1.6 graphing inside these log calculations here, we pretty much covered everything. Yeah, we did. Now, on the last note, I will write it one more time. Exponential function and logarithmic function are inverses of each other. And that is rooted in the idea that a to b equals c converts into log a of c is b. Oh, there is another question coming in. Yeah, there is a lag between what I say and when you guys see it. and then by the time you type, so now I have to go back to the previous problem. The question says, if the asymptote is at x equals 2, do you shift the x-intercept? The answer is yes, everything shifts, right? The original x-intercept is at 1. This is the original graph, right? The one that is a default ln graph or log graph, which you are memorizing just like you memorized x squared, you memorized x cubed, absolute value of x, square root of x, right? You memorized all of those graphs, and you are memorizing as well ln x basic graph. So basic ln x graph has a vertical asymptote at the y axis, and it has the x-intercept at 1. Now, we had to reflect first because of the minus. Once I reflected, because I'm reflecting on this axis, which is also the vertical asymptote, the graph reflected from the right to the left, creating the x-intercept to be -1. And now we are shifting everything 2 units to the right. So this did move 2 units to the right, because it used to be here, and now from 1 to 0 is 1 unit, and then another unit, so it is 2 units between -1 and 1. And the asymptote, which used to be on the y-axis, also moved 2 units to x equals 2 for the asymptote. So everything moves, every single point of the function moves to the right or the left or up or down when you are shifting it right that way. So all of them have to move as you go along. So I hope that makes sense, right? When we reflected, the x-intercept jumped at -1, and because we are shifting 2 units to the right, it ended up being at 1, where the original 1 was. But we got there by shifting. All right, exponential function and logarithmic function are inverses of each other, and I'll just say because of this, right? Conversion factor. So what do I do with this? Remember that for inverses we had the function composition, right? So we know from inverses, this is I believe 1.8, we know that function composed with the inverse will give us x, and inverse composed with a function will give us x. That means that we can have log base a of a to the b is just going to be b. Now you can check this using conversion. Here is your a raised to the exponent b is equal to the result. Yay. We also have that a raised to the log a of b is equal to b. Check. Log of a of the result b is equal to the exponent, and the exponent is also log a of b. So we check in either way, right? We get the same answer on both sides. Now that helps with calculations, actually. That helps with calculations. How much is log base 3 of 9? If you want to use the calculator, you have to use change of base. But hold on. Look at that formula up there. Log base 3, and I can write this as 3 squared. You see that? Stare at it until you see it, right? So 9 I can write as a base 3. And then the base 3 from the log and the base 3 from the exponent actually cancel out, leaving just 2 as the answer. Let's see. Log base 5 of 125. You write it as log base 5, and then 125 you write it as 5 cubed. So the answer is 3. Log of 10,000. So what do we know about log with no base on it? Waiting for the chat, and given the lag, I might be waiting for a long time. Yeah, there we go. Perfect. Log is base 10. Yes, log is base 10. So this means log base 10. Now 10,000 can be written as 10 to the 4th. So when they are the same by the formula up there, right? So this is what the inverse, right? How inverse kicks in to help us compute these things. Now obviously if you have something that cannot be expressed as the exponent like this, then sure, we have to use the calculator. But in some cases like this, right, it's nice to compute. So that's what we have. Now, what is ln of e? ln of e is going to be 1, because ln of e is the same as the log base e of e, and then that's 1. But how much is ln of e to the 6th power? That is going to be, again, log base e of e to the 6, and it's just 6, because the formula up there said so, right? It's the math rule. I mean, it's not the formula is saying this. It's the rule because you have the base, and now in function composition you have exponential with the same base. So they cancel. And we are going to use this a lot as we move on, especially in sections 3.4 and 3.5, and then it never goes away. Calculus is coming, right? So when calculus comes up, we are going to use this again, and we're going to use it a lot. Your Precalc 2, by the way, is mainly trig, so I'm not sure if you're going to see exponential function at all. It's a shame, but such is life. So I think we beat this one to death. in terms of logs. What I'm going to do on the bottom over here is I'm just going to put all of the formulas on the pile. And let's see. So first of all, a raised to the b equals c converts into log base a of c is b. We said that log base 10 of x is just log x, and we are using log on the calculator. Log base e of x is written as ln x, and that's ln. And we said that these are not special cases, these are not different logs. This is all the same as all other logs, except these two particular bases are the ones that nature likes. So all of our applications are in terms of these bases. And I gave you examples, go back in a video, right? So they're just, those are the ones that are used. Now, change of base. If you really want to calculate other bases, even though it's useless because we don't have them anywhere in application later on, then log of any base of any number is going to be log b over log a. And we can use the ln b over ln a. So either one. Cool. The next one, what is the next one? The next one is those cute formulas. They're also cool. So log any base, and when you have the same number, you get 1, and log any base of 1 is always a 0. Now you can prove those by using conversion, right? If you do the conversion, over here it will say a to the 1 equals a, and over here would say a to the 0 equals 1. So, you know, that's just to check, right? You can use exponential form to check your log formulas. Cool. All of the 1.6 transformations for graphs, 1.6 graphing. So we have f of x plus minus c, f of x plus minus c inside. We have the constant multiplying f of x, and then we have the f of negative x and negative f of x. So these work the same as in 1.6. I said that 5,000 times so far, because it is, you know, log is a function, and because log is a function, we have it obeys the same rules. And finally, 1.8 inverse. Where we said that log a of a to the b will give you b, and a raised to the log a of b will also give you b, and those are formulas that happen because we have these two to be inverses of each other, and the function composition would cancel logarithmic and exponential function, leaving just the number behind. And we had a couple of examples for that as well. So I am going to open homework for this. I will reopen the chapter 2 practice. You can always use study plan to practice anything. You don't necessarily need to have homework open. If you want to practice any chapter, any section, just go into study plan and practice whatever you want, right? Because study plan is the one that has all of the problems that are available in the software, and then homework is a subset of that. So homework has actually less variety and less problems than the study plan. Study plan has everything. Technically, if you do all of the problems from the study plan, you definitely did all of the problems on the exam, because exam also has to be created from the study plan, right? So if you are going to, sit there and do all of the problems, make sure you know all of them, right? Well, then you're definitely going to hit all of the problems on the test, right? Because study plan is where all of the problems are, and then you just pick some for homework, pick some for quizzes, pick some for tests, right? From that database. So if you go into study plan and you solve all of the problems, then yeah. Anyway. So you guys, regarding exam, you guys all, not all, you were divided between exam to be today and then exam to be next week. And I originally wanted exam to be as soon as possible, which is hopefully today, right? But the problem was obviously my MATLAB and being unreliable and not working for everyone. And I kept getting, videos and screenshots and all of these things where it's not loading things. My algebra students couldn't open the exams and so on. So what I am doing now is I am merging all of the exams to Canvas, which is always up. And then there will be no excuses, I can't open Canvas, because Canvas works for everyone all the time. But merging exams and doing all of these things and exporting and, making sure everything is working properly is taking me some time. So even though initially today's date for exam 1, because of the my MATLAB mess up, in terms of interruption of service and everything else, I had to push the exam for the next week. So we are going to have exam next week on Wednesday on Canvas, Wednesday, Thursday next week, which is the second highest voted dates. So we have to move it there because of the my MATLAB, and the quizzes for exam 2 should start tomorrow, right? Which means that I am going to post announcement for the quiz and exam, and then I will be just working the exam, right? I will be reposting the exam on Canvas so you can take. So your quizzes will be on my MATLAB, right? Your quizzes will be, your practice quizzes will be on my MATLAB, and your exam should be on no, the quizzes, that just way too much exporting and points and everything else to move the quizzes as well. There will be, moving 21. Each quiz is the same as the test, right? And there will be just moving all of those quizzes as well would be annoying. So quizzes will remain in my MATLAB, the homework remains in my MATLAB, only the exam, because exam is the biggest issue that we are having with this online class, right? You guys are still having full instruction because I am teaching every day. It's just on the live rather than in the classroom, but it's still, one-to-one interaction. Those of you interested are typing in a chat. You are present when I teach live, so we are as close as possible to the classroom experience with the method we have over here. The only annoyance is the test, right? That's the only annoyance. So I have to work out. I just see the question about the Canvas and timed exam. Yes, I am working on making sure that the exam is timed because we need to measure the knowledge, not right. Grade is not as important as what you learn in this course. Grade is actually useless completely. If you don't know these concepts, you will never, in 1,000 lifetimes, pass Calculus 1. Never, 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 right? So quizzes on my MATLAB will have unlimited try, and your exam should have one timed try. And obviously, if there are any students with accommodations, that will obviously be taken in consideration, because it's a law, obviously. That is going to be taken in consideration just like when you have the regular in-class exams. And in terms of the project, I'm going to upload that in Canvas. You guys will make since you can't hand in the hard copy, which is what I am always requiring from students, you will have to make a submission for that assignment in Canvas. You will attach the file in Canvas as an assignment. There will be assignment for project, and you will just attach your final project by the deadline. Deadline is always for my project is the final exam. So I will be posting that as well. I usually post it after exam 2. Now that we stretched exam 2 for additional 3 weeks almost, it's a little bit annoying, but yeah, I will post that, and the project will be there. So I will talk about that, and also I will be adding you all into the office hours, virtual office hours through Microsoft Teams. And those are, I just added my differential equations students, and I had my first run with, I believe 7 or 8 students were online at the time. And it went well. I had to add them first because they are the ones who have exam in 2 days. So the next class to add to office hours will be you guys, which I will probably do tomorrow morning, and we can have the first office hours maybe, let's say, Friday or something, and then office hours next week, obviously, at my regular times. I will be posting that in announcement as well. So keep reading the announcements, and I will let you know about the details. So we are aiming for quizzes to start tomorrow, 6 a.m. We're aiming for exam for Wednesday next week, so Wednesday, Thursday deal. I am aiming to have exam on Canvas. The quizzes will be in MyMathLab. Exam is the MyMathLab exam exported into Canvas, so we don't have interruption of service, so you guys can go in, do the exam, and submit, and be done. And what else? I think that's all. And the project will be posted as soon as possible. I just need to make sure that everything else is up and running for all of the classes, which pretty much it is. I just have this one stress, which is exams on Canvas. I just need to, once I solve that, everything else is set for the rest of the semester, and we're just gonna sail smoothly into the final and be done in a month. I will also post in Canvas at some point the pass no credit, where you will choose which option you want. The grade F does not exist for this semester, so if you choose to keep the letter grade you earn in this class, it will be counted towards your GPA. So if you score B on all of the exams, then you have B for the class. But if you don't like B, you can just choose not to have it listed, right? You will choose pass no credit in the assignment. There will be a special assignment for that posted in Canvas, and you will have to make that decision a couple of days after the final, right? So you will know what your grade is for the course, and then you will decide either to keep it, which will count, or you will decide to reject that grade, which will, in that case, not count towards your GPA. But we are going to, and yes, that's per class. So it's per class, so you will have to choose. If you're taking chemistry, math, and English, you will have 3 choices to make. So you will make separate choices for each one of those, and then you are moving on with the next. So I believe there is also a web page available on the college website that explains the details of it, and the college president also emailed everyone, making sure that everyone is aware of what pretty much all schools are doing, which is no Fs, and you can choose pass no credit, or you can keep the letter grade you earned, and the letter grades you earn are A through D. Right, A through D are letter grades that are available for this class. F is actually removed from the choice, so I can't even by mistake assign F this semester, right? Or as a joke, right? So there you go. That's it for today. I will see you all next week. Bye.